So we've set up now the twin paradox. You can see I've got some things covered up here because I don't want to get too far ahead of ourselves and distract ourselves from some of the things we'll be doing here. But this is twin paradox part 2. And remember how we set it up. And the paradoxical part here is that both Bob and Alice, here Bob, Alice takes her trip to the star 3 light years from Bob and then back again. Both of them see the other's clocks running slow, time dilation as we've done a number of times before, but when they get back, Alice is younger than Bob. And so Bob can understand, they say, oh, I can, as much as possible, can understand the time dilation effect. Yes, that's going on, and therefore Alice is traveling with respect to Bob, and so he sees her clock running slow and also running slow on the way back. We talked about, remember, the acceleration issue here. And in fact, we can analyze the twin paradox without having to do anything with acceleration, the general theory of relativity, and so on and so forth. We can understand it just from the concepts of the special theory of relativity. So Bob sees Alice go out and back again and understands that with time dilation, her clocks are running slower. She should be younger. But Alice sees the same thing for Bob. So the question is, why is Alice younger? That's the paradox. How can she understand that she's younger when it seems like maybe Bob should be younger? And so that's what we want to do in this part 2 of the twin paradox. And we're going to use our space-time diagram to see if we can understand it graphically. You can see I've added some green dashed lines here. We'll get to those in due time. But essentially what we want to do here is break this basic diagram up into 2 parts. We're going to look at the outbound trip, and then we're going to look at the inbound trip. So let's take a look at the outbound trip here. This doesn't take off too much of the diagram here. Okay, so what we've done, like we've done a number of times before, is we have put both of their space-time diagrams on the same plot, both Alice and Bob. So Bob is in black, Alice is in red. So we can see Bob's got the 90-degree angles. Alice, for a velocity of 0.6 c, we've drawn the appropriate angle of each of these. This is the x sub a axis. This is the t sub a axis. In fact, remember, this really is the world line for Alice. She's moving along the t sub a axis, and we can see that as she moves along, when she gets to 4 years on her clocks, she's at the star, 3 light years away. And on Bob's clocks, that reads 5 light years. In the next part, we're going to do this quantitatively. We're actually going to put the numbers in. So they do check out here, but in terms of 3 light years, velocity is 0.6 c. Clearly, Bob sees Alice go 3 light years, and it takes 5 years to go 3 light years at 0.6 c. And Alice, from the time dilation effect, the gamma equals 1.25 factor, takes her 4 years as Bob is observing her clocks. Now the key thing here to remember, we've done this before, is the lines of simultaneity. So the dashed red lines are the lines of simultaneity for Alice. The black lines, the horizontal lines, are the lines of simultaneity for Bob. And as we've noticed before, this can show us that both of them see the other's clocks running more slowly than theirs. So for example, if we just pick out when Alice's clock is at 4 here on her time axis, the line of simultaneity for, if she had her lattice of clocks, remember really the lines of simultaneity represent the lattice of clocks in each frame of reference. And so she has her lattice of clocks here all synchronized. And so when this clock here is at 4, all these clocks for her read 4. That's the definition of a line of simultaneity, of course. And line of same time. And therefore, she sees, if she takes a photograph right here, with Bob's clock in the photograph as well, she sees his clock is actually 3.1, 3.2, something right in there. So her clock is at 4 at that instant. In terms of the line of simultaneity, Bob's clock is at 3.2, say. So she sees Bob's clocks running slower than hers. In other words, hers, as she travels along here, her clocks have run through 4 years of time, and she's observed Bob's clocks run through only about 3.2 years of time. Meanwhile, Bob observes the same thing. His clocks are going 1 year, 2 years, 3 years, 4 years, 5 years, the lines of simultaneity. So the black dashed lines represent his lattice of clocks at any given instant in time. And so we can see when he gets up to 5 years, Alice's clock on that line of simultaneity is only at 4 years. And of course, it's because they're using different lines of simultaneity. Simultaneity is relative, as we've said many times before. So we can understand that from our space-time diagram here. So just to reiterate, this actually, the outbound trip is similar to things we've done before, but just to make sure we understand here. So here comes Alice. She's traveling along. And in Bob's frame of reference, of course, she's traveling on the x-axis here. And she gets to 3 light years out. That's where the star is. And then at that point, she's going to start her return trip. So really, this line right here, which is her world line traveling through Bob's frame of reference, is the same as this line right here, traveling out to the star. And we've just put the lines of simultaneity in and also the scale markings for Alice's clock and actually her x-axis as well. Okay, so that's the outbound trip. We see that when Alice reaches the star, Bob's clock reads 5, Alice's clock reads 4. And so then the next thing we have to understand is the inbound trip, back again. So let's take a look at that now. And actually, before we do that, I want to mention one thing here. One reminder, we've mentioned this before, but haven't used it as much as we've done this diagram, this combined diagram, and that is, this is a diagram for Alice, in this case, moving to the right with positive velocity. If we have a situation where the person or object or whatever is moving to the left, remember it's a different combined diagram. We still have, I'll just do it right here to sketch it, and then we'll see an exact diagram here. So we still have something like this where we have, in this case, T sub B. So this is Bob being stationary in his frame of reference. Then if we've got the other frame of reference moving to the left, we get something like this for the other axes. Let's even see if I have any red left here. Something like this and like that, roughly speaking. Okay, where this is TA and this is not XA, not T there. Okay. We haven't done as much with that just because normally we have things moving to the right. It's just easier to work with that one direction than can reverse things if we have to go to the left. But if we're going to do a combined diagram with something moving to the left, as Bob is observing it here from his frame of reference, then just think about this. Again, the T sub A axis here is a line of simultaneity. Not the line of simultaneity, is a world line for that object moving. Clearly, it's moving to the left on the x-axis. As time goes on, its x value is increasing negatively there. And then the lines of simultaneity, if we put those in, again, are always parallel to the x-axis. And so just roughly speaking, the lines of simultaneity are going to look something like that. And Bob's are still going to be the horizontal lines. And this is going to be a key point, actually, because what happens is when Alice turns around at the star, her frame of reference is changing. Instead of going positive velocity, now she's going in the opposite direction. And when that changes, her lines of simultaneity change as well. And so that's what we want to analyze now using a diagram that's going to look something like this. So let's take a look at that for the inbound trip. So now we're going to look at this part of the trip. Going back from the star, remember everything's really happening on the x-axis here. She goes out to the star, turns around, and comes back again. And this is the world line out, and then the world line back, and ends up at the planet again, if that's where Bob is. Okay, so we got this here. Here's what the inbound trip looks like. And again, it's useful for you to reproduce this. If you have graph paper, great, but the key thing is just get a general sketch of what's going on here. So here's what we've done. We've taken Alice out to 3 light years away, so now we're starting at 3 light years. Okay, so this right here is this segment of her trip back. And note, just like we had up here a minute ago, we'll look at this one more time. Note the similarity here between This is what we have, combined space-time diagram when something is moving to the left. Notice what we have here. Okay, so the x-axis going down like that, t-axis, t-sub a axis tilted to the left, and the lines of simultaneity. This is really why we have the x-sub a axis in this diagram, because we want those lines of simultaneity for her new frame of reference. One frame of reference going out, velocity going that way, now has turned around, coming back this way, has a new frame of reference. She's changed her frame of reference. So, let's see what we've got here. Again, we put the markings, scale markings for her. And once again, if we wanted to, you could look and see that each of them thinks the other's clocks are running slow. And what happens, though, as she moves back towards Bob position at 0 here, you can see moving that she ends up, at that point, when she gets back, her clocks have ticked off 8 total. In other words, she started, remember, to get to here, she went to 4, and then going back, it's just another 4. So that's very symmetrical that way. The question, though, again, is where does that extra time for Bob go? Because, again, Alice should be thinking, Alice sees Bob's clocks running more slowly than her clocks, and therefore she should think, shouldn't Bob be younger when I get back? Well, here's the key thing, and we've tried to bring it out with these dots here, the green dashed lines. Let's take a look at that. When she's at the planet, okay, from the outbound trip, she gets there, and at that instant, when she arrives, presuming she hasn't slowed down quite yet, so she's still going with velocity v toward the planet, her line of simultaneity is, with that frame of reference pointing back down here, Bob's clocks read 3.2 actually. Looks like 3.1, it's really 3.2 when we do it in the next part of the twin paradox video. So it points there, okay? As soon as she turns around and starts going the other direction, her frame of reference changes, her lines of simultaneity change, and note that, here's where she is. She's at the planet right there. So really this point and this point are the same if we combine the diagrams. It's really this point right here, when she's at the planet. And so in that instant of turning around, all of a sudden, she's in a new frame of reference with different lines of simultaneity. Her first frame of reference, lines of simultaneity, go down like this, and so when she's there, this green dashed line represents her line of simultaneity. As soon as she turns around, and we're assuming not quite instantaneously, but fast enough such that we can ignore the acceleration and deceleration compared to the long time of just going at constant velocity. As soon as she turns around, essentially what that acceleration, deceleration does is it puts her into a new frame of reference. She decelerates and then accelerates again very quickly up to her velocity of 0.6 c. So now she's heading back here, but she's in a new frame of reference. The lines of simultaneity now point this way. So look what happens in that few instants of turning around. Right before she turns around, if she took photographs of all her clocks and Bob's clock back here at the home planet, his clock would read 3.2. As soon as she goes through the process of turning around and then looks at her lattice of clocks and sees where Bob's clocks are back at the home planet, look where it is. It's up at 6.8, actually. Okay? So in that turning around procedure, as far as she's concerned, if she's observing Bob's clocks during that time, his clocks speed up from 3.2 here to 6.8. And that's where the lost time, as it were, comes in. It's during that turning around process. Because then, and as we'll see quantitatively in the next video clip, that then it just ticks off normally. She sees his clocks running at 3.2. So essentially on the outbound trip, she sees his clocks reading a total of 3.2 years, as we'll see in the next clip. And then on the inbound trip, she sees from 6.8 to 10 is another 3.2 years, while her clocks read 4 years on each leg. And then again, what happens is, though, so if you think about 3.2 years, she observes Bob's clocks running slow. Another 3.2, that's 6.4. So when she gets back, she'll say, Bob, I thought you'd be 6.4. You'd have aged 6.4 years while I aged 8 years. But again, that turning around, the switching of frames of reference is accounted for, or really the clocks then in Bob's frame of reference, or really Bob's clocks from Alice's perspective, from Alice's frame of reference, jump from 3.2 to 6.8. So when she does get back, Bob is 10, has aged 10 years, and she has aged 8 years. So what we want to do in the next video clip then is do this quantitatively with some of the procedures and machinery we've developed, time dilation and so on and so forth, the Lorentz transformation, and see if we can get the numbers to work out. Again, conclude that there's this jump when Alice changes frame of reference. There's this big jump in the timekeeping as she's observing Bob's clocks, and that's the key to understanding the twin paradox.